This is Barry Halverson with the Lake Management District Steering Committee for Lake Lawrence. Today with us we have retired Professor Jeff Tepper from the Geology Department at the University of Puget Sound, who's offered to provide our steering committee with a presentation on lake science, dissolved oxygen, pH, and other factors that go into that. And with that, I'm going to turn it over to Jeff to talk to us about that.
So the purpose of what I guess I'll talk about first here is understanding what controls oxygen levels in water in a lake and why that's relevant to the choice you might make regarding treating the lake for hazardous algal blooms. So one of the tools that you could consider is what's called zero-valent iron, which is basically just powdered metallic iron. And when you apply it, it's a powder. When it comes in contact with water, it basically rusts. So you wind up with a coating of iron oxide. So you have these little particles that have a coating of iron oxide, and that's a very reactive surface, which means that chemical reactions take place there, and one of those reactions is that phosphorus, if it's dissolved in the water, will stick to that iron coating. So when you use this product, what your goal is to have it sink through the water column, and as it sinks through the water column, any phosphorus that's in a dissolved form will stick to it, and then it accumulates on the bottom, so it's stripped the phosphorus out of the water, and then while it's on the bottom, it has a second purpose, which is to act like a blanket that intercepts any phosphorus that's coming out of the sediment on the bottom. And that's basically the same philosophy as any phosphorus sequestering agent. They've sort of got two purposes. One is to strip what's in the water as it's sinking through the water. And that's true of alum, that's true of phoslock, that's true of butyrosorb, all these different things. As they're sinking through the water column, they're supposed to sequester and extract phosphorus from the water. And then they lie on the bottom and they act as a blanket. The concern that sometimes is raised about using iron is that if conditions are very reducing, if conditions are oxidizing, then you have rust. And rust is iron oxide, and the phosphorus will be bound to that. If the conditions are sufficiently reducing, then the iron goes back from being 3+ to being 2+, and at that point it dissolves. So that's called ferrous iron, and ferrous iron is soluble in water. So if you've used an iron product and it gets to the bottom, but then it dissolves, it releases what was bound to it. That's not very effective. So the question is, when do you need to be concerned about the iron dissolving? And that's a question that's related to the oxygen, amount of oxygen that's present. So I'm actually going to skip to a different figure. Let's look at this one. Okay, so this one's figure 2. Okay, everybody see that?
Yes.
Yes. Okay, so I'll try to demystify this as much as possible, but it's a lot easier to teach if students ask questions, so feel free to do that. So what's on the vertical axis here, which is labeled PE, is a measure of how oxidizing or reducing the conditions are. So this is functions like pH. So pH is a measure of how acidic things are. And when pH is high, things are basic, and when pH is low, they're acidic. PE works the same way. So when the number is big, like 14 up here, conditions are very oxidizing. And as you go down the axis here toward negative values, things become very reducing. And what this diagram is supposed to show you is how oxygen levels in the water, or oxidizing conditions, change as organic matter is decomposing. So the main reason that oxygen gets used up in a lake is because there's organic matter. So there's dead algae, dead other plants. And when those decompose, the carbon in that material is converted to carbon dioxide, and that uses oxygen. So if you have a lot of undecomposed organic matter on the bottom of the lake, you'll tend to have low oxygen. So as that material decomposes, we're going to move from left to right across the diagram. That's just saying more decomposition is going across the diagram to the right. Okay, so initially, if there's dissolved oxygen in the water, decomposition is proceeding, but there's no change in how oxidizing the conditions are. And this is kind of the most important point of the whole figure here, is that dissolved oxygen is a buffer. And as long as there's any oxygen present, any dissolved oxygen, conditions are going to be the same in terms of how oxidizing it is. And that's very oxidizing. As long as you have any dissolved oxygen in the water, it's buffered to very oxidizing conditions. A typical, for water that's in contact with the atmosphere, dissolved oxygen is like 10 or 12 parts per million. That's so if you're decomposing organic matter, initially you've got plenty of dissolved oxygen, and while it's being used up, conditions stay the same here at this high PE value, something like 13. Okay, when we get to this point, we've used up all the oxygen. And then there's going to be a drop to less oxidizing conditions, and we're going to start a different reaction, which is again basically providing oxygen for the decomposition of organic matter. In this case, we're reducing manganese. And there's usually not that much manganese present, so that's not a very long step in the process. And then things are going to drop again. Each time you use up one of the oxygen suppliers, you drop to a new buffered condition. So this next step here is where nitrate is being reduced to ammonia. And then it's going to drop again. And the point I want to make is that it's not till you get down here where the PE is about 2 that iron begins to be reduced. And that's the point that you care about if you're thinking about using iron as a phosphorus sequestering agent. So let me just ask a question. Does it make sense to you that as long as there's any oxygen still present in the water, dissolved oxygen, then conditions are going to be oxidizing and all the iron's going to be in the oxidized state?
And during that entire time, the iron is collecting phosphorus or attaching to phosphorus.
Or it's already done its job and it's just sitting there with the phosphorus attached to it.
At the bottom of the lake.
At the bottom of the lake.
Okay.
But the important point I want to make is that, so iron is effective when it's in this +3 state, which is called ferric iron. It's going to be effective as long as it's in that state, and it's always in that state if you have any dissolved oxygen, because that's a buffer.
Okay. Is the organic matter in the bottom of the lake putting off oxygen or taking up oxygen?
No, it's consuming it.
It's consuming it.
Because what you're doing is making carbon dioxide.
Okay.
So carbon, C plus O2 oxygen makes CO2, and then
Right.
that's the breakdown product of the organic matter.
Okay.
So we need to have plenty of oxygen above your 2 or 3 number in order for the iron to maintain its properties of not dissolving and releasing the phosphorus.
Right, so we need to have, well, at a minimum, well, if you're above 2 on this diagram, you know you are fine. Because that's about the point where the iron begins to be reduced. So anytime you're above that, you're fine.
Okay, but that
And
doesn't equate to dissolved oxygen levels.
that's correct. That is not that. So any dissolved oxygen at all, whether it's in contact with the atmosphere, you'll be at about 10 parts per million. If you have 0.1, you still have dissolved oxygen. You are still up here because it's a buffer. I mean, sorry to keep saying that over and over again, but that was a concept I never understood when I took chemistry in college, but now I do, and it just means if there's any present at all, your conditions are fixed, and they are fixed at a very oxidizing condition.
So, if I understood that, any oxygen, however low, puts us in the good part of your graph.
Right. Any oxygen at all puts us up here at the top.
And so in a lake situation, and we've talked about the bottom of our shallow lake maybe having less oxygen, is there the possibility there is no oxygen down there? And then, segue maybe into...
Okay.
I don't know.
Okay. There is always the possibility of that. The data you got when you had Herrera study your lake, it was never at 0. It was as low as 0.4, which is not good for fish. We can talk about that later, but it was never 0. Now, one of the challenges is that when you're trying to measure dissolved oxygen at really low levels, there's always an analytical uncertainty. So if it measures 0.3, it might actually be 0.1 or 0.5. It might even be 0. It's hard to be really confident when you're measuring that levels that low.
And one of the things that we've been told by those that do the water testing for us, environmental health, is that with their probe, when it goes down, they try to keep it off the bottom so their probe doesn't go into the sediment.
Right.
But if they actually would put the probe into the sediment, the DO levels could be much lower than they are at, say, 6 inches above sediment level.
That's almost 100% certain. If you put the probe into the sediment, the dissolved oxygen is probably going to be 0.
Then how does...
And that's because...
Go ahead.
And that's because there is so much carbon in the sediment that wants to decay that it's sucked all the oxygen out, and that pore water, the water, so I'm going to assume it's okay to use the term pore water to describe the water that's in the sediment.
Yeah.
That has given up all the oxygen it has, and it may now be in the process of, so these other steps on this diagram, like manganese being reduced or nitrate being reduced, those things are going to start happening in the pore water.
Okay.
Now, I didn't talk about this, but if you get way down here, now you're in very reducing conditions, and now you're beginning to convert sulfate into sulfide, and that's what gives this hydrogen, or this hydrogen sulfide gives you that rotten egg smell.
Mm-hmm.
So if you're way down here, you will start to smell hydrogen sulfide, and that's probably happening in the sediment, but it's not happening in the water. I don't think there's been no. If you have dissolved oxygen, this can't be happening.
Well, Jeff, one of the things that we have happen at our lake almost every year is we have these eruptions of large portions of our bottom sediment, and they actually float up to the top and stay on the surface for a long period of time.
Yeah.
Is that because of the CO2 and the sulfur buildup underneath the sediment?
Probably. It's probably that carbon dioxide is being formed in the sediment, and you're making a big bubble, which has a hard time getting out, and so when it finally does, it just grafts up a big chunk of material.
Right.
So there's at least 3 gases that you can be producing in there. You could be producing carbon dioxide, which is the most abundant and most likely. If conditions are more reducing, you can start to make methane, which is natural gas.
Yeah.
And then hydrogen sulfide is also a gas, but that's probably not very abundant. I would guess that 99% of what's being produced down there is carbon dioxide.
Okay.
So in terms of caring for your lake and controlling algae, I don't think it's practical to try to control what's happening in the sediment. You cannot put enough oxygen into the system to decompose all the carbon that's in the sediment. You don't really need to. What you're interested in is what happens after material gets into the water itself.
Right. And the other concern that we have that Environmental Health and Washington Department of Fish and Wildlife have is that from about 5 meters down during about 6 months out of the year, our DO levels are so low the fish won't live in that area. They move to other areas of the lake.
Right. Okay, now so the reason for that is because once the lake becomes stratified, so it gets heated up in the spring and summer, so then the water near the surface is less dense. So you wind up with a situation where the water on the bottom is staying on the bottom and it's isolated from the atmosphere, and all this decomposition of carbon is taking place, so you use up all the oxygen. That water is very poor in oxygen then. That is, I'm going to say that you really can't prevent that by any reasonable process. I mean, that's just nature. You could dredge the sediment off the bottom, which would be extraordinarily expensive. You can't realistically add enough oxygen to that water to counteract all the carbon that's there. So I don't remember what the carbon content of your sediment is, but it's probably, let's just say it's 20% carbon, which is kind of low for a lake. That's 200,000 parts per million. And the most oxygen you're going to have in water, even if you enhance it, is something like 15. So it would take a lot of water with 15 parts per million to decompose 200,000 parts per million of carbon. So I think, I mean, I'm not a fish person, but fish are, I presume they are surviving in your lake by going elsewhere in the summer.
Right.
And I don't think there's any realistic treatment option that's going to fundamentally change that.
No, the concern is that, as you know, trout are, they prefer the colder water, the deeper water. Right. And during the summer months, the low oxygen levels below 5, I think, milligrams per liter, something like that,
right.
Doesn't allow them to survive in the lower levels. So they have to move to higher, which is warmer water.
Right.
Which stresses them.
Right. I stopped sharing it.
Yeah.
Okay. Well, the low oxygen issue to me is separate from the algal bloom issue.
Okay.
And we can, you can ask me questions, but one concern that has been expressed before about adding iron is, does that exacerbate the low oxygen situation? And the answer is, when you oxidize iron, you do use some oxygen. However, that's mostly happening up at the surface when you apply it to the water, and then it sinks to the bottom. It's already oxygenated at that point. And if you're doing this in this, early in the season when you're trying to get ahead of the algal bloom, the water is oxygenated at that point, and once it's rusted, it's not using any more oxygen. So I don't really think, in terms of maintaining fish habitat, that iron is a problem with that. I don't think it's going to go away, because I think you've got this carbon on the bottom, but I don't think adding the iron is a contributor to that.
If we applied iron and it goes to the bottom, and there's a potential of this low oxygen level situation in our lake, then we have thrown some money away when it reduces. And you mentioned other sequestering items like alum. Right. Would those be better choices then?
Okay, so 2 points. The first one is that I don't think your lake bottom ever gets to the point where iron would dissolve, because it has to not only use up all the oxygen, it has to go significantly beyond that, using up nitrogen and things like that, before it gets to a point where iron is dissolving. So that's point number one. The other products like alum and Foslock, those are not oxygen dependent. So they're not using iron, they're using alum is using aluminum, which also will, that has pH issues, but it's not a redox. It doesn't affect iron, affect the oxygen levels. And Utrosorb is a clay that's had lanthanum added to it. So it's, again, it's a reaction that binds phosphorus but does not depend on oxygen. So iron's the only one that uses oxygen. But that's how nature does it. I mean, nature is most lakes, naturally, iron is the main sequestering. It's where the phosphorus tied up if it's not in organic matter. When you apply alum, you're applying it as aluminum sulfate. What happens when you put it in water is that the aluminum attaches to OHs in the water, and that forms a solid, a flock. They call it a flock. Little particles that sink.
Right.
And the phosphorus sticks to those sinking particles. But what's left out of this is that when you make that aluminum hydroxide flock, you're profoundly changing the pH of the lake. You're taking all this OH out, and so the lake becomes way more acidic unless you apply something else to buffer it.
Right.
And so you have to apply two things. They have to be applied in the right proportions, and you're left at the end with all the sulfate and the sodium that was added as the buffer. Those things are left in the water still. So because those are not part of the sequestering process. So it fundamentally changes the composition of your lake. Now, depending upon how fast the water is exchanged, it may go away in a matter of months. But and you do have to monitor aluminum. Aluminum is not very soluble, so it mostly doesn't dissolve. That's true of iron as well. It basically does its job, but doesn't stay. It's not dissolved in the water.
It sounds like your belief system is that the iron is a more natural product to our lake. It doesn't have this potential pH balance issue. It's been around for forever, I suppose. Why is it that people developed all these other chemicals then?
Oh, that's a really good question, and I don't entirely know. The primary concern with iron is the one we've talked about, which is that under reducing conditions, it would dissolve. I went back and looked at the Washington, permitting guidelines to see what did they have to say about iron and where did they get their information. And it all seems to have gone back to a 1981 EPA study, which when I looked at that study actually doesn't say anything about zero-valent iron. It was a report on various lakes where this had been applied, and for the ones where they'd used zero-valent iron, they said no data. So I don't really know quite why that report has been so influential. But the main concern has to do with it dissolving and releasing its bound
phosphorus.
Yeah.
That is one of the key things. They say that when it gets down to the bottom and zero dissolved oxygen content is 0 or below, then it'll eat magnesium and nitrates and then dissolve and release the phosphorus back into the water.
Okay, so I guess one point I would like to leave you with is that although that is true, that is not true just because dissolved oxygen went to 0. It has to go way past that to get to the point where, the second point I would make is that it's not like you flip a switch and all of a sudden iron's not working.
Yeah.
It's a gradual process, and the effectiveness of the iron depends on the ratio of iron to phosphorus. And so the observation in natural lakes is then when that ratio is more than 10 to 1, iron basically is permanently binding the phosphorus.
Right. And I gave you our data sheets, right. and the indication was that the ratio was really low.
Your ratio is really low. That is true. So there's a reason why it's not working. Well, what we can say is that compared to other lakes in the area, Lake Lawrence has relatively low iron in the sediment. So that's not helping.
Okay.
You mentioned earlier that there wasn't a lot we could do about the stratification and then the density levels of the lake that occur during the summer.
That's just nature. I mean, the water gets warmer and as it begins to warm up in the summer, and it becomes less dense, and so you can't control that. And hand in hand with that is that the water on the bottom becomes isolated from the atmosphere, and if you have carbon on the bottom in the form of organic matter, it will consume that oxygen, and you will wind up with a lake that's stratified not only in temperature but also in oxygen. And almost every lake is like that. The only exceptions would be really shallow lakes where wind can stir the water. And there's, I think some cases like wakeboarding and things can stir up the water, but you'd have to have a lot of wakeboarding to really change that story.
So you mentioned the turnover of the water.
Mm-hmm.
Our lake, I would think, probably is a more stagnant lake because it's only when we get above a certain level that we get an outflow.
Okay.
So it's not like some lakes. We don't have a flow constantly through the lake.
So as far as you know, your lake is mostly fed by surface runoff. Is that true? Or precipitation?
And a couple of springs.
Okay, do you know how much the springs account for the inflow?
They say it's about 7%.
Okay. So groundwater in the summer is probably colder than the surface of the lake. That's my guess. So when that water comes into the lake, it's going to tend to pond up on the bottom.
Mm-hmm.
But it's probably oxygen poor because it's groundwater. So you're not really helping oxygenate the water by having springs on the bottom.
Correct. It's just bringing phosphorus into the lake.
If your groundwater has phosphorus in it, it's coming in. I mean, that's what's happening at Stilicum, is that lake is mostly fed by springs and groundwater input, and that's got very high phosphorus in the groundwater.
Yeah.
And so it's feeding the blooms there.
The testing that has been done, is the information I sent you, shows that about 85% of our phosphorus is in sediment. About 7% is brought in through the springs, and the rest is through overland flow into the lake, and from animals and birds and geese and stuff.
Right. Okay, well, one comment I would have about that is I'm not sure that 85% is a meaningful number, because a lot of that is just bound up in the sediment.
Correct.
If it's bound up in the sediment, it's not contributing to the problem.
Right.
Now,
one of the things that we've been told is that the dissolved reactive phosphorus that is in the water column is what is stripped from the water column with the iron powders.
That's correct. That's true of all products should do that.
All sequestration products do that.
Every sequestration project should do that while it's sinking to the bottom.
Right. And it's the particulate matter containing phosphorus, like the algae, that alum, Metafloc, Utrizorb WC, which is a new product not authorized in Washington State. Metafloc's not authorized in Washington State right now either. Are the ones that take out the particulate matter. None of the others do that.
I don't know about those products, but I would say that if you are timing your application right, you time it before the algae has grown.
Correct.
And then you don't have to remove the particulate matter.
Right. You strip it early spring time frame.
You strip it early spring. So you strip it early spring. There's sort of two options. Stripping it early spring is the more economical one.
Mm-hmm.
And if you have a long residence time for your lake, which it seems like maybe you do, then you should be okay for the rest of the season if you've removed that phosphorus early on.
Okay.
Now at Stilicum, the residence time is shorter, I think, than at Lawrence. So there's we're treating the lake at the vents there to intercept the phosphorus that comes in. But not this past year, but the year before, we decided it was possibly there's going to be a bloom in July, and we didn't want a bloom on the 4th of July, so we did a second treatment after there was some algae. And what we did in that case was first use an algicide to kill the algae,
Mm-hmm.
wait about 2 weeks till it's decomposed, it's released its phosphorus, and then you apply the sequestering agent.
Right.
So you can do this later in the season. It just means you have an added expense of using an algicide.
Right.
Okay.
Oh, go ahead.
You go ahead.
I was just wondering, so if you apply, how often would you have to apply iron? In the situation we've cleared the water, it's now sequestered the 85% or this large amount of phosphorus that's coming from our lake bottom has been sequestered. Is there a lifetime for this? I mean, do you have to redo it in how many years?
So that's a really good question for which I can't give you a numerical answer. Once you've stripped it from the water column, if you don't have a lot of replenishment from external sources, meaning the groundwater vents or overland flow, then your only remaining source is the sediment on the bottom. And this diagram that's up here now shows you what happens when you have when you've applied iron on the bottom. So can you see this diagram now?
Yes.
Yes.
Okay, so this bottom part of the diagram represents being in the sediment. And the top here labeled oxic represents somewhere up in the water column. And this is the boundary between the sediment and the water column, which is sometimes called the sediment-water interface.
Right. Usually a couple centimeters.
Yeah, just a couple cents. It's quite thin.
Yeah.
Okay, so down here at depth, when you're deeper in the sediment, and deeper might only mean 10 centimeters,
Mm-hmm.
conditions there are really reducing. Iron is dissolving, and it's moving up toward the surface, as is phosphorus and anything else that was dissolved. So those things are coming out of the bottom. If there's enough iron here, they might be intercepted at the bottom. But let's just take a worst case scenario where you don't have enough iron in a layer on the bottom to intercept the phosphorus that's coming out. So that's what's represented by diffusion here. So iron is diffusing out of the bottom, it's dissolved, it's coming out of the bottom. At some point in the water column, and probably not very far off the bottom, it's going to encounter conditions that are oxidizing enough that the iron is going to oxidize back to the 3+ state, and it's going to precipitate. Because you don't have to have dissolved oxygen for that to happen. You just have to be more oxidizing than the boundary where iron dissolves. Now, when it oxidizes, it's going to form a solid. It's going to precipitate. It's going to form little tiny particles that are called colloidal particles. They're minute, but they're solid. And they will bind the phosphorus that's in the water, and then because they're solid, they'll sink back to the bottom again. So you wind up with this sort of continuous loop here in which iron dissolves, comes up here in the water, and up here into the water, oxidizes, forms little particles, binds the phosphorus, takes it back down again. And as sediment accumulates, this boundary layer that has all this iron in it just keeps moving upward. So you're not really in my mind, you're not trying to prevent any phosphorus from leaving the bottom. You're just trying to make sure that whatever leaves the bottom doesn't wind up where it can be utilized by algae. And iron is coming out of the bottom with the phosphorus, so it's naturally providing what's needed to bind it as soon as it comes in contact with any water that's oxygenated.
Okay. So
Does
when
that make sense?
It does, but when they tell us that our lake has about 6,700 to 7,700 pounds of phosphorus in it, is that
in the sediment?
Well, I'm assuming that it includes sediment and the dissolved reactive phosphorus in the water column.
Okay, well, it has to be almost entirely in the sediment because the levels of dissolved phosphorus in the water column are measured in parts per billion.
Okay.
So when you get above 20 parts per billion, you have enough nutrients that then you begin to worry about having an algal bloom. And if you have something like 50 parts per billion, that's really high. The concentration of phosphorus in the sediment is measured in parts per million, which is 1,000 times higher. So I don't remember the numbers in your lake, but if you've got, 50 parts per million phosphorus, which is low, that's 50,000 parts per billion. That dwarfs what's in the water.
Okay, so when they talk about products per pound, even with zero valent iron or alum or anything else, they talk about you need so many pounds of alum, so many pounds of Utrosorb G to strip the phosphorus and sequester it. And they give you a number like $2 million to do that, like they did in Black Lake. And I'm sure you're familiar with that story.
Not really.
Okay, well, they spent $1.5 million, one application in 2021. They stripped the water column, they sequestered all the phosphorus in the bottom of the lake, and they haven't had an algae bloom since.
Okay.
The algae is growing because you got Black River that flows through there, so obviously there's more phosphorus coming into the lake, but it hasn't increased the amount of phosphorus in the water column to the extent that it's caused the harmful algal blooms yet.
Right. Okay.
So with Lake Lawrence, we don't have, like Stephen said, we don't have a influx of water through a river or stream or an outflow except for a couple months out of the year.
Right.
It's all coming from precipitation, overland flow, and vents in the bottom of the lake. So we have a relatively, other than that, it's the same old thing. It's your decaying plant material, it's your plants and birds and animals, etc., which is going to accumulate over time. But I think what Janice was trying to get at is if we sequester what's in the water column with an application of whatever it is, alum, lanthanum, iron, and it pulls the phosphorus out of the water column, there's no guarantee that it's going to pull all the phosphorus out of the water column, from what I'm understanding.
Well, I don't think it's never going to go to zero.
Right.
So for this to work, it depends on an iron surface coming in contact with a phosphorus molecule. I don't think your goal is to take it to zero. Your goal is to take it down low enough that you don't have an algal bloom.
Correct.
And I think, all I can say is that when we were applying it at Stillicum, we would then sample the water afterwards and send it off to a commercial lab, and it was below detection, which was 10 ppb. So
I guess the other question I would have, Jeff, is what is the metric that can be used from the different water analysis that's done by our environmental health department, which I've sent you since 1990, we've been doing these tests, 6 months out of the year, to determine what the phosphorus levels are based on Secchi disk and all the three different areas. And what is the metric that we need to really look at? Because I have not been able to find a common denominator in all of that water analysis data that would lead me to say, okay, this test last month indicates that we're on an uprise and we're going to have an algae bloom within a couple weeks.
Well, I think that the best thing for that's the SECI depth, frankly. The problem with, if you're measuring SRP, dissolved phosphorus,
Right.
if it's already in the algae, it looks low, but that's not a good sign. It means it's already been metabolized and you've already got the algae. So
Right.
a better measure than that is total phosphorus, and I don't know, I can't remember if that's something that they routinely measure or not.
We do.
Okay, so total phosphorus and SECI depth, and then knowing something about the species of algae that are in the water.
Like microcystin?
Like Microcystis and Anabana and these other ones.
Yeah. The two that we get are microcystin and anatoxin A.
Okay. So now what we've done at Stilicum is a combination of mostly relying on SECI depth because if you're sending, we can do our own phosphorus analyses, but any commercial one takes weeks to come back, and so it's not really a realistic time frame if you're trying to prevent a bloom.
Exactly.
So we look at SECI depth, we do an on the boat phosphorus analysis, and then we look at the algal population, what's in it, and if we start to see microcystis and the SECI depth has been shallowing, then we start to think about more frequent monitoring and whether we need to do something to prevent a bloom.
Okay. How do you test for the phosphorus on the boat?
We have a little portable spectrophotometer,
Okay.
costs $150. It's, I think it's pretty good. The problem is we're not a certified lab, and some people don't, not everybody is meticulous in doing their own analyses, so it's hard to trust somebody who just did it on the boat.
Correct.
But, we've done a lot of analyses and compared them with the commercial ones, and they're usually pretty good. So the commercial lab stuff is mainly done so we can, document this for people off the lake who want to know how it's going and would like to be confident that the analyses are good.
Okay. So with Lake Stilicum, go ahead, Frank.
No, that's some sort of a spectral analysis, the tool you were just talking about.
Yeah, you add a reagent to the water and it forms a blue color.
Okay.
Depending, and the darker the blue, the more phosphorus you have, and you pop it into a little spectrophotometer which passes light through that tube and measures the darkness of the blue, basically, and that's converted to concentration.
Okay.
But otherwise, iron is an inert compound. It's not, it doesn't, it rusts, but it doesn't dissolve in the water, and it doesn't form any toxic compound, and it has no adverse effect on, fish or anything else. So it shouldn't, none of these, as far as I know, if they're applied correctly, should have an adverse effect except alum, which alum I think is a much more fraught with risk option because of its effect on pH and because it has a lingering effect on the water chemistry.
So Jeff has done a great job of helping me understand this and also of selling me on the iron option. So why should, Barry, maybe you can help with this as well. Why would we be considering anything else than the iron option?
Well, there's a lot of options. I sent Jeff a copy of our, what I call it's our decision matrix. Jeff, you got it. It was that
I did, right.
spreadsheet, Janice, that you helped me with and Frank helped me with and a couple others. But I want to compare all the different products in order to make a good decision for our lake.
The risk, if I'm understanding this, if at the bottom of we apply the iron and all of a sudden we have this less than 0 at the bottom of the lake, and so the iron starts to reduce, you have still up this cycle of it hits an oxygen
Is that still up?
Yeah, and it falls back down. So one, I'm curious as to why they're all so there's apparently a risk, right, that with this low oxygen the iron will dissolve. But what is the risk? That it releases the phosphorus. We're not worried worse off than we were before we started. And if the iron oxidizes, when it falls down, does it pick up that phosphorus again?
It does.
So why are we so concerned about it hitting the zero thing?
Well,
In
I
this whole
can't
thing?
answer that question because I'm not concerned about it. So I think there are. Part of this goes back to this 1981 paper, which, it is true that iron under reducing conditions is soluble, but zero DO is not reducing enough for that to be an issue. It has to go below that. So if you think back, let me go back to this. Well, with that diagram that had different amounts of redox conditions on the vertical axis,
Right.
and you had to go down to where hydrogen sulfide is forming and things like that to get iron to dissolve in a significant way. That's just not happening at the surface of your lake. Your lake is too shallow. We can see this process happening at Spanaway. So in Spanaway, Ecology, Herrera, other companies have done water analyses just like you guys have done. And in the bottom waters, there's very high iron, but the SRP is below 10 ppb. And the high iron tells you that's coming out of the bottom. There's iron in the analysis that could possibly be dissolved in the water, and that's because it's formed these little particles that are going right through the filter. And there's almost no phosphorus in dissolved form on the bottom at Banaway.
And SRP, you're referring to soluble reactive phosphorus?
Right.
Okay.
That's the dissolved form of phosphorus.
Okay.
There are different products of iron, and part of what's different is their surface area. And so if you have a very fine powder, it sinks more slowly and it has more surface, so it's better for stripping the water column. If you have something you want to stay in place on the bottom, like you want to put it right on top of a vent, then you use something that's more like fine gravel. It sinks fast, but that stays in place on the bottom, and the vent doesn't blow it out of the way. It's pretty economical to just put coarse iron on a vent. It's not a big area.
Mm-hmm.
It may not need to be done more than once every couple of years, if that. And 7% is 7%.
Right. Okay. Anybody have any last-minute questions for Mr. Tepper?
When they apply the iron, I assume they hire a contractor to do that. Is there anything from preventing us from doing it?
Yes.
Okay. Enough said.
Yeah.
I would just add one thing. I think Janice asked about like how long this would be effective or something like that.
Yeah.
And I don't think I gave you a really complete answer, but I think the only way to know that is, basically to keep, track over time. The so-called, what's called the magic number for the iron to phosphorus ratio in natural lakes is about 10. And if you're above that, then it seems that phosphorus release is pretty well controlled. And the samples that I saw that you had analyzed were varied, but most of them were under 10.
Right.
You're already at, let's say 6 or 7%, so you could calculate how much iron you need to get up to 15 iron to phosphorus ratio, and that ought to last a while. All I can say is that at Stilicum, the stuff we applied at the vent seems to still be working 2 years later. So I think it's a reasonable expectation that an initial application of whatever product you use would be effective at stripping out what's in the water column until that's replenished. And in the case of iron, should work on the bottom for at least a couple of years. I was kind of surprised to find out that really Stilicum is the first lake where this has been done, in a sort of organized way anywhere.
Anywhere
So
in
we're
Washington State, yes.
Yeah, and even beyond, there's not a lot of this been done anywhere,
Mm-hmm.
which is ironic because, I shouldn't use the word ironic, but it's surprising because iron is routinely used in groundwater cleanup. So like dig a trench and put a bunch of iron in the trench to intercept a contaminant. And groundwater is very oxygen poor. So the only difference is that there's a huge amount of iron there. But, I think for a variety of reasons, you should have all your different products evaluated on the same basis. But I just think there's iron has been underutilized, I think, in lakes where it's appropriate.
And you've got the numbers, Barry, and I don't remember them off the top. Wasn't iron one of our lower cost items?
It is.
Okay.
The iron particle, in order to be effective, has to develop a rusty coating. And it's that rusty coating that the phosphorus sticks to. But over time, that rusty coating flakes off, and it exposes a new surface to get rusty all over again. So there's a life to this material that is beyond just its initial application times. Because every time you expose new, fresh iron to the water, you rejuvenated it, and that is an ongoing process, and until some point when it's either all the metallic iron is gone, you've used it all up, or it's become so coated with other stuff that it's not effective. But it renews itself.
That makes me think about the plants that are growing in our lake. So we've applied the iron, let's say, and we've sequestered, and now our plants over the years are growing and dying down, and they are effectively then going to cover up this iron deposit. Talk about that.
Well, that's where I think that this cycling process comes into effect. So if the plants, and I think algae is probably going to do I don't know, let's just say if organic matter buries your layer of iron, and the iron dissolves, and it then diffuses upward into the water column, it becomes oxidized and reprecipitates, it just keeps landing on the top.
On the top, huh?
So and a way that I know that this happens is because I've done a lot of projects when I was teaching where we would core a lake, collect a sediment core. Mm-hmm. You know what I mean by that?
Yes.
Yeah.
And then we would analyze, each student would get 3 slices to analyze them. So we'd have 50 1-centimeter slices. And inevitably, the top of the core is iron rich compared to everything else. And that's because it's diffusing up to the top, coming out of the water, into the water, and then precipitating back down. And that's a moving interface. So I think as long as there's some iron in the system, it automatically gets to where it needs to be.
And I really appreciate your time today, and the classroom instruction was beneficial, I think, to all of us.
Absolutely.
This was so helpful, I can't tell you. I'm very excited about the information you gave us.
Well, thank you very much, Professor. We really appreciate your time, and we've taken too much of it already.
Kind of miss being in the classroom, so thank you.
Okay, have a good night.
All right, you too.
Thank you, Jeff.
All right, thanks, Jeff.
Have a good evening.
Thank you.
We need